Hi everyone, in this video we are going to practice predicting ionic formulas, and the way we're going to do that is by looking at different sets of elements, specifically a nonmetal and a metal, and we're going to try to predict what their chemical formula or ionic formula will be when they come together and form that perfect electrostatic interaction with an overall neutral charge. So let's start off with this first problem. We have three different examples, we have three different pieces, and we're going to try to create some kind of molecule with sodium. So go ahead and predict what the chemical formula or ionic formula will be for each of these three situations. Go. All right, did you get an answer? Hopefully you did, but if you didn't, please do not get frustrated. This is something that takes a little bit of time, but more importantly, practice in order to get it right. So the very first thing you do is figure out what the overall charge is going to be on each element. So sodium wants to be a cation. It wants to have that overall +1 charge, and that's just because it's in group 1. It's an alkali metal. So every single one of these sodiums is going to have a +1 charge. Now, oxygen is in group 6, so it usually has a -2 charge. Nitrogen is in group 5, so it usually has a -3 charge, and chlorine is a halogen, so group 7, so that usually has a -1 charge. And now all we have to do is take these charges and swap them for their superscripts, okay, just like that. So essentially what would happen is if sodium and oxygen came together, is you'd end up with the overall ionic formula of Na2O, and then 1 is really what you'd put, but we don't write 1s in chemistry, so you just erase that right there. So you'd end up with Na2O, okay? We'll work on the naming in a later video. All right, now for this one, again, we swap, so the 3 comes down here at the bottom, the 1 comes down here, and so we end up with Na3N. Simple as that. And then the last one, hopefully you could see that one and right away go NaCl. Some students want to write Na1Cl1, but that's just not conventionally how we do it. We drop the ones, we ignore it, we imply that there's a 1 if it's there, and so NaCl would be the perfect one. All right, so hopefully that makes sense. Let's try something a little bit more challenging, this time using phosphorus instead of a different one. Go. All right, did you get an answer? Hopefully you did, but if you didn't, don't get frustrated. The first thing we have to do is figure out what these charges are on our cations and anions. So let's look at phosphorus first. Phosphorus is located in group 5, directly under nitrogen, so all three of these phosphori, are going to have a -3 charge. Now, potassium is also an alkali metal, so it's in group 1. This will have a +1 charge. Calcium is in the alkali earth metal, so that's going to have a +2 charge. And then aluminum is in group 3, so this just has a +3 charge. Now, the biggest trick here is that you have to remember that you always write cation first, then anion second. So these are for your ionic formulas, meaning the positive component goes first, the negative component goes second. So for all of these, before we even do our little flip thing, we need to remember to rewrite this, so it's going to be Kp, not Pk, okay? That order is very, very important. Now we need to assign our charges. We see that the phosphorus is going to make sure that we have 3 potassiums in order to have a balanced charge, and the potassium has the +1 charge, so that's why there's nothing written here. All right, same thing, we write our calcium first. These are all going to have a 3 because that's what the charge is of our phosphorus. Calcium has the +2 charge, so that's going to be to the bottom of the phosphorus. Same thing here. So now we have to switch our subscripts. One goes here, one goes here. They are both 3. If they're both the exact same charge, you don't write it out. So remember, cation first, anion second. They're both 3s. We could write this. That's just not how we do it with convention. I actually don't even like looking at that. I would prefer for you to write ALP, just boom, done. All right, hopefully that makes sense. Let's try something maybe a little bit more challenging when we throw in some polyatomic ions. Go. All right, did you get an answer? I'm going to fly through this one because we've kind of done this a couple times now. Calcium is in group 2. It's an alkali earth metal, so all calciums are going to have a +2. This is definitely our cation, so this is going to be the first section. And then our oxygen, group 6, -2 charge. Now our sulfate, it has an overall charge for the entire polyatomic ion of -2. And then phosphate also has an overall charge of -3 for the overall polyatomic ion. So again, just like before, you just flip your charges, okay? So if it's a -2 for the oxygen, that becomes the subscript for the calcium. Now the first thing we're going to see is that both of these have a 2 charge, so +2, -2. So when we write this out, instead of writing Ca2O2, we're just going to write calcium oxide, just like that, CaO. Same concept applies here. So the 2 goes here, the 2 goes here, but it's the same exact charge, so we don't actually write it out. So this just goes CaSO4, okay? Plain and simple. Last one, we have our calcium first. Now we have to apply these charges. It's not the same, so we can't ignore it. We have to write it out. So calcium 3, and then our phosphate, PO4. Now the big important thing is the phosphate is an entire section, it's a group by itself. So we can't just write PO42, that doesn't mean anything. Does that mean 42 oxygens? What is that? We cannot write that. You have to do PO4 parentheses and then put the 2. So this is saying that we have 2 phosphates overall for every 3 calciums. All right, let's try one more, and instead of using the anion as the polyatomic ion, let's use our cation as the polyatomic ion. Same thing as before, just show me the ionic formula. Go. All right, did you get an answer? Hopefully you did. This one was a little bit more challenging because we added a polyatomic ion to our cation, but the same concept goes as before. The first thing we do is figure out our charge. So for our ammonia, it's +1 the entire time. That's never going to change. Sulfur is in group 6. It's directly under oxygen, so this has a -2 charge. Arsenic is actually in group 5, so it's underneath nitrogen, underneath phosphorus, and that is, well, it's actually underneath phosphorus, I should say, and so that one is going to have a -3 overall charge. And then hopefully fluorine, we're quite comfortable with this one now. It's a halogen, it's group 7, definitely has a -1 charge. So just as before, we're going to take these charges and switch them. So this +1 becomes to the bottom, the -2 goes to the other side for our ammonia, so we write this out. NH4, it's a polyatomic ion. If we were to write this 2 here, that would mean we have 42 hydrogens. That doesn't make sense. What we do have, though, is 2 ammonium polyatomic ions. And then simply we just put our sulfur, and then we just have one of those, so we would write a 1, but we know by now that we don't write our 1s. All right, next one. So we're switching our charges again. So again, we have our NH4 and then 3, okay? We have to imply that we have 3 ammonium ions, not we have 43 hydrogens. That's something totally different. And then we just have a 1 for the ammonium, so nothing fancy here, just plain old arsenic. Last one, it's a 1 and a 1, meaning we don't have to do anything with our charges, so this one we just write out as NH4F. That's it. Hopefully this makes sense. We're going to do another video to practice actually naming those to come up with a nomenclature, so stick around. Have a great week. Take care of yourself and drink water.